we are going to build an intuitive visual understanding of conservation of mechanical energy, including translational kinetic energy, potential energy, and rotational or angular kinetic energy. Then we'll apply it to a classic example, a solid cylinder rolling without slipping down an incline, and we will find its speed at the bottom. First, the three forms we will keep track of. 1. Translational kinetic energy, 1/2 mv squared. 2. Gravitational potential energy, mgy. 3. Rotational kinetic energy, 1/2 I omega squared. When no non-conservative forces like air drag or sliding friction do work, the total mechanical energy is constant. That total equals translational kinetic plus rotational kinetic plus gravitational potential. So initial equals final. Now, the example. A solid cylinder is released from rest at the top of a ramp of height h. It rolls without slipping down to the bottom. For a solid cylinder, the moment of inertia is 1/2 m r squared. Let's draw a clear, to scale diagram, and then animate the rolling. Energy bookkeeping is simple if we choose the bottom as our zero for potential energy. At the top, speed is 0, so no kinetic energy. All energy is mgh. So initial energy equals mgh. At the bottom, height is 0, but now the cylinder both translates and rotates. So final energy is 1/2 mv squared plus 1/2 I omega squared. And because there is no slipping with static contact, omega equals v over r. For a solid cylinder, I equals 1/2 m r squared, plugging that in turns the rotational term into 1/4 mv squared. By conservation, mgh equals 1/2 mv squared plus 1/4 mv squared, which is 3/4 mv squared. Solving gives v squared equals 4/3 gh, and v equals the square root of 4/3 gh. Let us watch the cylinder roll. The contact point does not slide, which is exactly what omega equals v over r means. The rim speed at the bottom matches the ground speed. We'll roll from the top to the bottom along the ramp. To make the energy split crystal clear, watch the energy bars. At the top, all energy is gravitational potential. At the bottom, that same total has been converted into two parts, translational kinetic and rotational kinetic. For a solid cylinder, the split is 2/3 in translation and 1/3 in rotation. Key ideas to remember: mechanical energy is the sum of translational kinetic, rotational kinetic, and potential energies. If no non-conservative work is done, that total stays constant from start to finish. Rolling objects share energy between translation and rotation, and the moment of inertia sets the split. For our solid cylinder, we found v equals the square root of 4/3 gh. Final result for a solid cylinder rolling without slipping from height h, v equals square root of 4/3 gh.